The group of people assembled here from far and wide really brings home the fact that, we're really in the middle of this very new and exciting field of physics that's emerging, which lies at the confluence of many diverse areas of theory, but also at the confluence of theory and experiment. And here I really mean experiment both in the actual lab with quantum simulators and also numerical experiments with classical simulators. So, there's many deep connections between these different areas, some of which will be discussed in this workshop. But one unifying theme that's emerged is the study of many-body dynamics of closed or isolated quantum systems, okay? So these could be systems of spins, electrons, Rydberg atoms, trapped ions, what have you, right? The constituents of a black hole. And in all cases, the system is going to be very strongly interacting. And very generally, it can also be very highly excited, okay? So it's at very, very high temperatures. So most of the usual tools of analysis that we rely on that have been developed over decades in the study of many-body quantum theory simply don't apply in this limit, okay? And the study of many-body quantum dynamics raises a bunch of interesting questions ranging from the measurement problem to the foundations of quantum statistical mechanics. And while I hope some of these will be covered in the course of this workshop, in this talk, I'll mostly be coming at this through the lens of quantum statistical mechanics, okay? And indeed, a question that will be central in my talk is what the late time states of isolated many-body systems look like. And in particular, whether such a system can bring its subsystems to thermal equilibrium at very late times, okay? So this question of thermalization and isolation is seemingly somewhat paradoxical, because under unitary time evolution, all quantum information is preserved forever. Unitary time evolution is reversible, right? There is no bath or reservoir to dump the quantum information into. On the other hand, the approach to thermal equilibrium looks like a seemingly irreversible process because things settle down and are described by a few variables like temperature or pressure, and it seems like memory about the initial condition is then forgotten, okay? So at this very general level, for the non-experts in the field, this issue of thermalization and isolation is actually very deeply connected even to the black hole information paradox. Because if you think of the black hole as a quantum mechanical object undergoing unitary time evolution, then again, there can be no loss of quantum information. On the other hand, if the Hawking radiation from a black hole only cares about a small number of parameters like mass or charge, then seemingly the information falling into the black hole seems to be lost forever, okay? So again, I'm going to be using this lens of many-body quantum dynamics to draw connections between these various areas, okay? So starting with the question of thermalization and isolation, an issue that's been at the focus of a lot of activity for many, many years, particularly over the last decade, is whether an isolated system can bring itself to thermal equilibrium, okay? So what we now understand is that even though unitary evolution preserves all memory about the initial conditions forever, this information can get mixed up or scrambled in very, very non-local, experimentally inaccessible degrees of freedom, so that if you go in and make measurements only on some small local subregions, then it can still look like the rest of the system can act as an effective reservoir or bath for the small subsystem and bring it to thermal equilibrium at late times, okay? So systems that do this are known to be thermalizing, but a lot of excitement has come from a class of so-called many-body localized systems that never reach thermal equilibrium and retain memory about their local initial conditions forever, okay? So you could prepare an extremely non-generic initial state, evolve it under its own dynamics. These are, again, these are generic, strongly interacting systems, okay? They're disordered. There's nothing very, very fine-tuned about this class of models. And in this class of models, I could prepare some very special initial state, say, which has all the atoms in that one corner of the room. And even if you wait infinitely long, local memory about that non-generic initial state is remembered forever, okay? And the phase transition between thermalizing and many-body localized systems continues to be an area of very, very active interest this is a new kind of dynamical phase transition that involves a singular rearrangement of the entanglement properties of the system. So ideas from quantum information actually play a very important role in understanding this phase transition. And it's really unique because it's on one side of this transition, quantum statistical mechanics holds, and on the other, it doesn't, right? So it's a transition that involves a restoration of statistical mechanics, okay? So, good. So when I was asking you this question about whether an isolated system can bring subsystems to thermal equilibrium, I gave a very coarse-grained yes-no answer. Okay, systems which do this are thermalizing, systems that don't are not. So let's add a little more structure to this. Even within the class of thermalizing systems, you can have systems that reach thermal equilibrium very quickly. Okay, and so on accessible timescales. I'll leave it open what accessible means. But if you were an experimenter and you were doing some experiment, you could see that things basically settle down and agree with what you would expect. On the other hand, you can have classes of systems that take extremely long times to thermalize. Okay? So on these long time scales, these systems could look localized, for instance, and it is a major experimental challenge to distinguish between systems that are truly many-body localized for asymptotically long times versus systems that just have some very, very long-lived regime that looks localized, but that eventually does thermalize. Okay? More generally, even if the system doesn't look localized in these extremely long time scales, it could nevertheless display other kinds of intermediate or pre-thermal regimes that could be interesting in their own right. Okay? So this is what happens on very, very long time scales. And indeed, another question that we can ask more crisply is, what are all the possible asymptotic dynamical universality classes? Okay, so if I'm not making this distinction between accessible and extremely long, but I only care about infinitely large systems at infinitely late times, I can ask in this setting, what are all possible dynamical universality classes that can exist? Okay, so, and what I'll tell you about today is a new addition to the class of dynamical universality classes that are out there that are not just thermalizing and not just many-body localized. Okay, so by this point, I've spent a significant fraction of my career working on localization. So why do I find this interesting, right? So perhaps most fundamentally, this is a conceptual issue, right? Like the breakdown of thermalization represents a new outcome in the late-time dynamics of isolated quantum systems. Much of modern physics is based on the assumption of statistical mechanics. Indeed, almost all theories of phases and the transitions between them rely on equilibrium statistical mechanics. But these are classes of systems that never reach equilibrium. So all of that large body of knowledge that we've en masse just doesn't hold. Okay. And in fact, what this immediately presents is the opportunity to get new kinds of phenomena that may be forbidden by the strictures of equilibrium thermodynamics, right? So thermal equilibrium imposes all sorts of conditions on what's allowed and what isn't. And once you step away from that, new kinds of things that we haven't even imagined might be possible. A paradigmatic example of this is the recently discovered many-body localized time crystal, which was thought to be impossible in equilibrium, but finds new life in this out-of-equilibrium setting, right? And more practically, to connect with the themes of this workshop, localization is a way to tame the relentless tendency of highly excited interacting systems to tend towards decoherence, right? So localization can slow down or stop this decoherence altogether. And of course, this is the primary challenge that any new kind of quantum technology has to address, right? So for all of these reasons and more, the quest for general mechanisms for robustly and provably breaking ergodicity continues to be a major research direction in the field of many-body dynamics. Okay, so in my talk, I will be presenting a new mechanism for breaking ergodicity. So let's step back and take note of what are some existing mechanisms for ergodicity breaking, right? So there's perhaps the most well-known is the theory of integrable systems. So these are systems that have extensively many local commuting integrals of motion. As a result of all of these conservation laws and integrals of motions, the dynamics of these systems are very highly constrained. So they don't go to thermal equilibrium in the usual sense. But these integrable systems are pretty fine-tuned in parameter space. You need to make lots of things line up just right so you can get these different conservation laws, okay? What I was telling you about just right now is many-body localized systems. And what's really special about them is that they're not fine-tuned. Okay, so they're robust to perturbations. They're pretty generic disordered models. So this is a whole phase, a whole dynamical phase of matter that can look localized. And one of the best, most useful phenomenological descriptions of many-body localization comes from this idea that MBL phases are characterized by extensively many emergent local integrals of motions. Okay, so once again, you have many, many degrees of freedom that are conserved and that are local, that constrain your dynamics and prevent thermalization. But now these degrees of these conservation laws become emergent rather than explicit, which is connected to the stability of MBL. Okay, what Misha told us about in the morning are some recently discovered classes of systems that loosely go under the name of many-body scars. Okay, so this is roughly an intermediate class with the coexistence of thermal and non-thermal behavior. So depending on what classes of initial states you start with, the typical behavior may be thermalization, but you can also prepare experimentally accessible different states at the same temperatures, and these look like they never reach thermal equilibrium. Okay, so the general mechanisms for what causes scars and when we might expect systems to show scars, these are all still very much under debate. But from everything that we can tell, these systems also appear to be fine-tuned, and just weakly perturbing the system, even within the class of systems that have been seen to show scars, immediately destroys this phenomenon. Okay? And I should mention that there are some known ways for embedding these non-thermal states by hand into a many-body system. You can always cook up very special fine-tuned models, but we're really interested in kind of robust phases of matter that break ergodicity. Okay? So what I'll be presenting today is a new mechanism for localization that comes from the shattering or fracturing of Hilbert space. Okay? And in fact, what I'll show you is that only two commuting constraints are provably enough to shatter Hilbert space into exponentially many dynamically decoupled sectors. Okay? So even if you have these two conservation laws, say a Hamiltonian which obeys these two conservation laws will look block diagonal, but now you could go in within one of these symmetry sectors that are set by the conservation law, and you find that nevertheless there's exponentially many emergent dynamical subsectors that aren't able to talk to each other. Okay? These subsectors have a wide distribution of sizes. Some of them have only one state in them, so if you start off in that state, it just looks localized forever, it can't go anywhere. Other sectors are very big, so if you start off somewhere there, it does mix up and thermalizes within this subsector. Okay? So with this mechanism, you actually get phenomena that's reminiscent of both many-body localization and quantum scarring, because you have some states that really remain stuck forever, like many-body localized systems, and you have some coexistence of thermalizing and non-thermalizing states. Okay? What I'll show you is that this mechanism that I'll discuss is completely robust to temporal noise. Okay, so in MBL, usually you start with some time-independent Hamiltonian, and you have to maintain that same Hamiltonian forever. If there's noise or in the couplings of the system, or if the system is changing in time, that's usually enough to destroy many-body localization. Okay, this mechanism does not care about that. It is robust to temporal noise, and it does not require any spatial inhomogeneity like disorder like many-body localization does. Okay, all you need for this particular example that I'll discuss is that these two conservation laws be obeyed and that your dynamics be local. Okay? What's very rare is that in all of these classes of systems, exact results or proofs are extremely hard to come by, but this has such an easy proof that I can give it to you in 2 slides, and I will. So this mechanism is rigorous. There's nothing to worry about with rare regions or higher dimensions, the kinds of things that people who study MBL do worry about. Okay? And the cleanest example of what I'll be talking about is provided by a so-called fractonic model, but the phenomenon is more general. Okay? And
2 plus energy, or you don't need the energy?
I don't need the energy. Okay? And you might say that this looks quite artificial, but actually, the reason I'm presenting this at this location is that there are very natural experimental realizations that are as simple as ultra-cold atoms in a tilted potential, something that people have been studying for a very, very long time. Okay? So again, this represents a new mechanism for robustly and provably breaking ergodicity. So what are fractons? The models that I'll be telling you about are inspired by fractons. So these are a new class of models that display many remarkable features that don't generally go together in some one class of systems, okay? So these are models whose elementary excitations are localized, but then composites or have restricted mobility, but the composites may be mobile. At finite temperatures, these systems often display glassy dynamics. There are many exactly solvable fracton models in 3 dimensions, for example, Haas code and the X-cube model. These were usually written down with motivations from quantum information considerations, like they form codes that are souped up generalizations of Kitaev's storic code, maybe not generalizations, but inspired by similar, they have similar features. They have properties that look both topological and geometric. And there's descriptions for these models in terms of higher rank gauge theories, okay? And these higher rank gauge theories, for instance, conserve both charge and dipole moment. That's one way in which this could come about, okay? So in this talk, despite the title, I'm not really going to be talking about fractons per se, but more fracton-inspired models. And what I'll show is that these 2 conservation laws of charge and dipole moment is enough to give you this kind of shattering-induced localization. Okay, so what do I mean by fracton-inspired models? Okay, let's do the simplest possible model we can. I just have a one-dimensional system. It's a chain, okay? On every site, I can have a qubit or a qubit. This can be a system of bosons. It can be a system of fermions. There's just some local U1 charge that lives on every site. In a spin system, this is a spin 1 system, so you have a minus state, a 0 state, a plus state, okay? In general, the minus and plus will represent the bottom and top of the values that a local U1 charge can take. And then I'll assert that both a charge is conserved, which in this language looks like z sub x, the sum over z sub x over all sites, and that the dipole moment is conserved, okay? And that's it. So these are just two commuting conservation laws. And this already immediately tells you that charges are immobile in the system, okay? Because if you start with a charge somewhere, there's a charge of 1 and a dipole moment of r, depending on the location r where that site is, where the charge is. But now if you try to hop the charge either to the left or the right, even though the charge is conserved, that hopping will change the dipole moment and is disallowed, okay? So you already have different symmetry sectors that are broken up by dipole moment where these charges don't move around, okay? On the other hand, if you have a composite, like a dipole with a minus and a plus together, then this dipole is mobile and can move around freely, okay? And more generally, charges can move by hitching a ride on dipoles, okay? So if you have this charge, it can hop to the left and emit this dipole to the right, and that's consistent with the conservation laws, and then this dipole can move away, okay? So you can already see that the dynamics are restricted even at the level of what the symmetries will allow you to do. But I'll further show you that even states that should be able to talk to each other just under symmetry considerations are forbidden from doing that, okay? So to make this even more concrete, what are the classes of models I'm thinking of? You know, these could be static Hamiltonians. So I could just consider Hamiltonian systems that explicitly have some kind of charge or dipole symmetry. This can have all sorts of terms. This is some kind of pair hopping term. So the dipole symmetry actually looks like center of mass conservation. So you can just build models like that. And even more generally, I can consider models, and I'll describe what I mean by these, of random unitary circuits. Okay, so these are circuits where these have proved to be very useful for understanding many universal features of quantum dynamics. These are toy models which build in locality and unitarity, but take away all other structure. Okay, so everything that would make your problem hard to solve, you can kind of abstract away. Okay, into a framework like this. And what you could do is, with these toy models, you can make them random in space, you can make them random in time, you can make them uniform in space, so you can play with various classes of models, okay? So indeed, something that my collaborators and I had done a few years ago was to consider what these random circuits look like when they're dressed with an extra conservation law, okay? So instead of choosing these unitary gates to be completely random, you could give it a bit more structure, build in a conservation law, and this allowed us to give a very concrete and microscopic answer to the question of how reversible unitary time evolution can give rise to diffusive or dissipative hydrodynamics. And this diffusive hydrodynamics was the hydrodynamics of this conserved charge, okay? So what we can do now is consider generalizations of these circuits with conservation laws, but instead of just building in charge conservation at this local gate level, we can build in charge and dipole conservation, okay? So this is why, to go back to Daniel's question, for these circuit models, I can make it random in time, so energy doesn't need to be conserved, and you can just have gates that locally conserve charge and dipole, okay? So now for my two-line proof for why you get exponentially many sectors, okay? So the setup is I'm considering the most general models with charge and dipole conservation, and some finite spatial range L, okay? And now if you go in and prepare initial states, which basically what you could do is just divide your system up into chunks of length L, and then in each chunk, either fill it with pluses or minuses randomly, okay, doesn't matter. Then what happens is when you act with a given gate, this gate either lives entirely within a domain of all plus charges, but now this gate is locally seeing a state with maximum charge, and it can't make any rearrangements because charge is conserved. Or this gate straddles one domain wall, and it locally sees a state of maximum dipole moment for this given charge because all the pluses are to the right of all the minuses, and once again, it can't do anything, okay? So all states of this kind, of which there are 2 to the L over L, are all strictly localized, even though there are only order L cubed symmetry sectors, okay? So even though you have different states with the same values of charge and dipole moment, under local dynamics, they cannot talk to each other, okay? So we can now build up different, so these were states that are strictly inert, strictly localized. You prepare any such state, it goes nowhere under the dynamics. But you can now also build up states where you can start with some inert states and embed into them active regions. So these are regions which are not frozen in this way. And usually when we study many-body localization, we really worry about effects where putting in some kind of thermal bubble into a localized system could just eat up the entire system. But in these systems, you can set it up so that you can surround this active region by shielding regions and then contain the effect of them to some given section, okay? So now not only do you have states that thermalize or don't, but within a given state, you can have regions that in time look like they reach equilibrium, whereas others just remain stuck at whatever they started with for all times, okay? And by doing this, you can build up sectors of various sizes. So I don't want you to understand the slide, but it's just, the message is just that this can be generalized to higher dimensions by requiring conservation of all components of dipole moment and or higher multipole moments like quadrupole, okay? And then for experiments, there are actually very clear physical realizations that can realize this. Because what you could do is, if you have in one dimension, suppose you have a system, this FH is supposed to refer to Fermi-Hubbard, fine, it can be anything, it can be Bose-Hubbard, but you have some Fermi-Hubbard model, you stick it in a tilted potential, you can note that this tilted potential directly couples to the dipole moment, okay? So as you tune up the tilt, you're actually making the term in a model, you're adding a term to the model which has the dipole moment, and you're increasing its strength, okay? And of course, if F was infinite, if you added an infinite tilted potential, then the dipole moment is strictly conserved. But if you make this very, very large, I'll show you on the next slide, the dipole moment can still look conserved for some very, very long time scale, okay? And on those time scales, you can get phenomena that conserves charge and dipole. You can do this in 2 dimensions with incommensurate tilts, and you can try to engineer quadrupole conservation with weirdly skewed quadratic potentials. But in all of this stuff, you know, these are very accessible. And in fact, I'm working with Wasim Bakr's lab to actually do some of this. This is not far off in the future, it's now. And as I said, the main challenge is that in real experiments, the conservation of Q and P is only approximate. And these effective approximate models that you get instead of being strictly local, have all sorts of tails in their interactions. But you can nevertheless use ideas from pre-thermalization to get long-lived regime with charge and dipole conservation, and you can get signatures of shattering in the strong initial state dependence of your dynamics. So to summarize, formulating all possible dynamical universality classes is a fundamental research direction. I showed you one new mechanism, which was really simple, but nevertheless allowed you to robustly achieve an intermediate class with both localized and thermalizing states. And there are many open questions, both theoretically and experimentally, in building on this new way of getting localization. Yeah.